This is a great section where we get to talk about Gauss-Jordan elimination, and we can't really talk about it without talking about who it's named for. This is Carl Friedrich Gauss. He's a German who comes up with the method, and then Wilhelm Jordan, another German, sort of improves on the method. And they're immortalized in mathematics for this method. Gauss is immortalized for a lot of other things in mathematics too. So just a little bit of remembering of what we've already seen, that when we have a system of linear equations, there's the three elementary row operations that we're allowed to do. You can swap two rows, you can multiply a row through by a constant, you can add two rows together, and it preserves the original solution. So all of those are legal to do, and they're helpful to do to be able to get the solution a little more clearly. And then we also talked about the number of solutions that are possible to a system of equations. You can either have exactly one solution, number of solutions possible. You could have many solutions, like an infinite amount, or you could have no solution. And those are the only three possibilities when we're confronted with a system of linear equations. It's not like you could have 5 solutions. You're either going to have one, infinitely many, or no solutions. I also put a picture of these stairs on this first page. It'll be kind of a symbol of the work that we're going to do, so that'll help us remember visually what Gauss-Jordan elimination can look like. When we say that there are different possibilities for how many solutions are possible, I want to go over the names of, you've probably seen this before, but if there is exactly one solution, that's sometimes called a unique solution. And if there are no solutions to a system, then the system is sometimes called inconsistent, like it's not solvable. So you'll see that word. And so let's say inconsistent system. And if there are many solutions to a system of equations, then that's sometimes called a dependent system. So when you see these words, they're all talking about the types of solutions possible for a system. And now one of the really big ideas of this section is the idea of reduced echelon form. The textbook calls it reduced echelon form, but you'll also see it some places, like on your calculator. A graphing calculator might use the word reduced row echelon form, so you'll see it as RREF on your calculator. A program that will use Octave Online also uses RREF. So be careful about this, because unfortunately, the acronym REF on your calculator refers to something else. So I'll try to be clear, and we'll go through an example on your calculator, but the text calls it reduced echelon form, but it also, another name for it is reduced row echelon form. I haven't even told you yet what reduced echelon form is, but I'm just going to throw you into a bunch of matrices. One of these matrices is in reduced echelon form, and the other 4 aren't. So think for a minute about this stair-step pattern and looking at these. Maybe you can already rule a couple of them out. Like I say, I haven't even told you what it is yet, but we want to look for some patterns. And so the answer is this one is in what we're going to call reduced echelon form, and none of these are. So let me tell you what reduced echelon form is and why these guys fail. There are going to be 4 criteria to be in reduced echelon form, and the first one is that if there are any rows of zeros, they need to be at the bottom of the matrix. So let's see, we run into a problem. I think one of these had, yep, right here, this guy had a row of zeros in the middle. So that's what disqualifies him. The next criteria is that the first non-zero element in each row needs to be a 1. And yep, this guy right here has a problem right here. The first non-zero element in that matrix is a 3, so that disqualifies him. The third trait of a reduced echelon form matrix is, that we want all of the ones from row to row, we want the ones to the right of the previous leading one. And that's, you're going to get this sort of stair-step pattern here. And I think there's one guy that disqualifies himself by messing this rule up. and it's, yeah, right here. This matrix, the second and third row need to be swapped out to get itself into reduced echelon form. And the last rule is you need to have zeros above your leading ones. And so this last matrix right here, it should have a 0 there. And you could create a 0 there by adding, like, you know, -5 times row 2 to row 1, and that would create a 0 there. So let's make sure this guy follows all the rules, the one that we said was in reduced echelon form. 0 rows at the bottom. Yep, it's right there. First non-zero element of each row must be a 1. Looks like that passes. 1's to the right of the previous leading one, for sure. And 0's above leading ones. This is the one that takes some work, usually, to get. But here we have a leading 1, and we've got a 0 above it. Here we have another leading 1, and we have zeros above it. So this matrix is interesting because this 2 right here, totally legal, but it doesn't have a 0 above it because it's not a leading 1. It's not that first element in a row. Before we start our first example, this little note, in our first section we did all the calculation by hands, all those elementary row operations, but starting with this section from now on to the end of the class, we're definitely going to use technology, a graphing calculator, or some type of software on the computer. So that's good news. So here we're going to take this system of equations and we're going to solve it. We'll use a calculator, but first we'll put it in a matrix. Okay, I've got it in the matrix here, and now I just want to put it in reduced echelon form. My calculator, which today I'm going to use my TI calculator, it calls it reduced row echelon form, so I definitely want to look out for the REF on my TI calculator, not the REF. So in just a second, I'm going to switch over to my TI calculator, which the face of it looks like this. And the keys I'm really interested, there's a teeny tiny matrix. It's a second button above the x to the -1 button. So we're going to use this, and you'll need your second button. We'll use quit sometimes too, so look out for these keys as we work through this problem. So the very first thing I'm going to do is go to the matrix menu and enter my matrix. I hit second matrix, and then I can either have a name, math, or edit. I'm going to edit matrix A, and the first thing I'm going to do is tell it the size of matrix A, and it is a 3x4 matrix. It looks like 3x4 is already there, and I've got another matrix. Wait a minute, this is actually the matrix that I want to put in. Okay, but if it weren't in there, actually let's go in and say that we were starting with not 0. Clear that. Let's say that I had to start with a 1x1 matrix. The very first thing I would do was say, well, there's actually 3 rows, enter, and there's actually 4 columns, enter. So now I have a fairly empty matrix. I'm just going to type over all the zeros. So 1, enter, 2, enter, 1, enter, 7, enter. It automatically goes to the next row for us. And then 2, enter, 4, enter, 3, enter, 18, enter. Okay, so I've entered my matrix, and this step you got to remember, you got to quit. You got to get out of that menu. Your calculator now knows that that's matrix A. So I got out of it, but now I'm going to go back into the matrix menu, and I'm going to do some math. And the math I want to do is not RREF, I want to do not REF, I want to do RREF on A, reduced row echelon form. And so I tell the calculator that that's the math I want to do, and then I'm going to go pick up that matrix. And I go to names this time, and I say, hey, I want to do that to matrix A, and hit enter. And that's it. I've got my reduced echelon form, and what the TI calls reduced row echelon form of matrix A. Great. The TI calculator put my matrix in reduced echelon form for me, and I didn't have to go through all those steps of the 3 elementary operations. Interestingly, I ended up with a row of zeros at the bottom. So we're going to try to interpret what that might mean for the solutions. I'm just going to start by rewriting what this row represents and what this row represents, and we'll talk about what this row represents. So the top row is just saying 1 times x1 plus 2 times x2 plus 0 times x3 equals 3. This statement here. And the second row says 1 times x3 equals 4. Third row gives us really no information, 0 equals 0. But this does tell us that we are in a dependent system, and these are going to lead us to an infinite number of solutions. It's not like the unique solution just popped out. All we have is a relationship between the variables, and we're going to try to construct the solutions from those. So this is a dependent system, and the real key to being able to write what the solutions look like is we're going to write the leading variables in terms of the other variables. What the heck do I mean? So the leading variables are like x1. I mean, that's kind of like the head honcho variable. And those leading variables are like the leading ones. So I've done that. I've written the leading variables in terms of other variables. So here's x1, and I just moved the x2 term over to the other side, but we know x1 equals negative 2x2 plus 3, x3, it stays as it is, equals 4, 0 equals 0 gives us no information, so we don't even bother writing it. Now what may be a new skill for us is we're going to use a parameter to describe the solutions, and the parameter is going to allow us to describe x1 in terms of x2. So we say let x2 equal r, then we know that x1 is negative 2x2, so negative 2r plus 3, x2 equals r, and x3 equaled 4. That was just a holdover from, and then this is how we're going to describe the solutions. And r can be any number. We can plug in 1 for r, negative 3 for r, 17 for r, and it will generate a solution to this system. There are infinitely many, and they all follow this form here. So this is how we'll write the solution to this system as an ordered triplet, negative 2r plus 3, r4. This is the solution set, and r can be any real number. So I just moved that solution set over here. Now I'm going to look at some specific examples, like let's say let r equal 0. What happens? Then that particular solution would be negative 2 times 0 plus 3. R is 0, and x3 is still 4. And so let's check this and see if it even works in the original system. So 3, 0, 4 is 3. This is 0, so 3 plus 4 equals 7. Yes. Is 3, this is 0, plus 2 times 4, so that's 8. Is 3 plus 8, 11? Yes. Is 2 times 3, which is 6. This is 0. 6 plus 3 times 4 is 12, equal to 18. Yes. So this is a valid solution to the system. So this solution totally checks out. It's real. It's a real solution. Let's try another one. Let's keep it simple. Let's say let's let r equal 1. Then if r equals 1, what does this pattern generate? It's negative 2 times 1 is negative 2 plus 3 is 1. R is 1. And then 4 stays as 4. So let's go check this solution and see if it works. I want to see if 1, 1, 4 is a solution to this system. So 1 plus 2 is 3, plus 4 is 7. Yes. 1 plus 2 times 1, that's 3, plus 2 times 4, so 3 plus 8 is 11. Yes. 2 times 1 is 2, plus 4 times 1, so this is 6, plus 3 times 4, that's 12. So 6 plus 12 is 18. Yes. So, good news, this too is a valid solution, and we could keep going and going and going. You could generate, obviously, infinitely many solutions to the system this way. There are infinitely many solutions to our system, and they all follow this pattern here. So now our strategy is, when we're solving a system of equations, we're going to put the system in a matrix, find the reduced row echelon form, and then we have to interpret the solution. And this is sort of the new thing, maybe the new thing, especially when we have a dependent system, being able to interpret that solution. Our second example is this one. We're going to solve another system of equations. Okay, we put the system in a matrix. I went ahead and did the reduced row echelon form in my TI calculator, and this is what I got out. This row of zeros down here at the bottom tips us off that we're in a dependent system, so we're probably going to have to write the solution using some parameters. And we're going to follow that rule that we used in example 1, writing the leading variables in terms of the other variables. We've got a leading variable right here and right here, so we'll do that next. This top row tells me that x1 plus 3x3 equals 4. The second row tells me that x2 plus 2x3 equals 1. And so now I write those leading those leading variables in terms of the other variables. So x1 on one side all by itself is being described in terms of x3. x2 is also being described in terms of x3. So we're going to use x3, we're going to use a parameter for x3, and then we'll be able to write the solution to this system. So the magical thing is we let x3 equal this parameter r. Then we can say x1 equals negative 3r plus 4, x2 equals negative 2r plus 1, and x3 equals r. And so this right here is our solution to the system of equations. So this right here is how we would write the solution. That would be your final answer. I always like to do a little bit of a reality check. So I'm going to say, let's see, I'm going to say, let's let r equal 3. If r equaled 3, then the solution would be negative 3 times 3 is negative 9 plus 4. And that is negative 5. If r equals 3, then this right here is negative 2 times 3 is negative 6 plus 1. And that is negative 5 also. And if r equals 3, then that third element is just 3. So is this really a solution? Let's see. I'm going to do some of this in my head here. So here's what I say is a solution to this system. So 3, let's look at the first row. 3 times negative 5 is negative 15, plus 15 is 0, and plus 3 times 3 is 9. Yes, so let's take this and go into the second row. Is 2 times negative 5 is negative 10, plus 5 is negative 5, plus so negative 5 plus 4 times 3 is 12. Negative 5 plus 12 is 7. Yep, that works. And we'll take this and plug it into the bottom row. 3 times negative 5 is negative 15. Negative 5 times negative 5 is positive 25. So negative 15, positive 25 is 10. Minus 3 is 7. Definitely works. So let's just do a quick review of the logic of this problem. They ask us to solve this system. When we put it through and get the reduced echelon form, the row of zeros tips us off that it's a dependent system. I use my strategy of writing leading variables in terms of the other variables right here. And I know I'm going to have to use a parameter because I don't know explicitly what numbers they are, I just know the relationship between the variables. I let that x3 equal the parameter r, and then I'm able to write the other variables in terms of that r, and I get this final solution. This is the set of all ordered triplets that will work for this system. There's an infinite number of them. I did a little tiny check just to make sure I believed it. If this was on an exam, I could get the solution, and then I could do a little check to make sure that I didn't make an arithmetic error somewhere. As we go on to example 3, one note that we need to mention is you may need more than one parameter to describe solutions in a dependent system. This time, the solution set, or this system of equations that we're going to solve, is this right here. I went ahead and put that system of equations in a matrix. I had my calculator do reduced echelon form, and this is what I got out. And this time I actually got 2 rows of zeros, but I went ahead and wrote, interpreted the first line and interpreted the second line. And the next thing I'm going to do is write the leading variables in terms of the other variables. So doing that, this is what I get next. x1 is going to be something expressed in terms of x3 and x4, and x2 also is something expressed in terms of x3 and x4. So I need two parameters, and I'll use r for x3 and s for x4. And once I do that, I can write x1 in terms of r's and s's, just using this line and using the fact that x3 equals r and x4 equals s. I can also write x2 in terms of the parameters, and then here are x3 and x4 as the parameters. And so I have my solution. This would be the answer if it was an exam question or a homework question. Here's your answer. I'm going to do just a little check. And I'm going to let r equal 0 and s equal 1. So putting those in for r and s, I get that negative 2 times 0 minus 1 plus 7, 3 times 0 minus 4 times 1 plus 1, and 0, 1 should be a solution, which means that 6, negative 3, 0, 1 should be a solution. So this should work for any equation in this system. Let's just look at the first one. 2 times 6 is 12, minus 4 times negative 3, so that's 12 plus 12. It's 24. This is 0. Minus 14 is 10. That one checks out. And I'm not going to show it right now, but it should work for these also. That was a good feeling that it worked for this one. If I was on a test, I would probably check these to make sure it worked and that my arithmetic was right. We've spent a lot of time looking at some examples of dependent system, but sometimes we get an inconsistent system. And how would we even know that we had one based on the matrix? We are going to solve this system, and it's going to end up being one with no solution, and we're going to figure out what tips us off that a system would have no solution. So I put the system into a matrix. I did reduced echelon form, and this is what I get out. And let's just go ahead and translate this matrix back into equations. So this says that x1 plus 2x3 equals 0. Okay, this one says that x2 plus 3x3 equals 0. And this last line says that 0 equals 1. So this is the tip-off right here. We've ended with a false statement. This can never be true, so the system has no solution. This is an inconsistent system. When you come up with a false statement like this, 0 equals 1, inconsistent system. And this is what it'll look like. That last row will be 0 equals 1. There is no solution. And we just end there. And that's the answer. You just have to state that there is no solution. We're going to pause on the examples for a minute and talk about a really important definition that will follow us through the end of the course. This definition is a system of linear equations is homogeneous. So this is the new word. If all the constant terms are something. So think of the constant terms of a system of equations. And if all of them are 0, then what you have is called a homogeneous system of equations. So when all constant terms, on the other side of the equal sign are 0, you have a homogeneous system. So for our last example, we're going to solve this system of equations, and all of these constant terms here are 0, so it is a homogeneous system. So I put the system into a matrix, and I performed reduced row echelon form, and this is what we get out. Okay, so what I'm going to do is I'm going to rewrite each of these rows of the matrix back as an equation. So this is interesting. I had this reduced echelon form. There was no row of zeros though, but it looks like I've got a dependent system. And this is because I have more variables. I've got 4 variables and only 3 equations. So if a homogeneous system has fewer equations than variables, there will be infinitely many solutions. Let's go ahead and use a parameter to take these and be able to write what the solutions look like. I'm going to write all the leading variables, x1, x2, x3, in terms of x4, so I'll let x4 equal the parameter r. And once I do that, I find that x1 equals 3r. I've just taken this over to the other side of the equation. x2 equals negative 2r. and x3 equals r, and I can write the solution set. And so the solution should look like this. This is what I would write as my solution to this homogeneous system: 3r minus 2r, r and r. Any vector that follows this pattern will work for this system of equations. So one question to ask you guys is 0, 0, 0, 0 in this solution set? And yeah, of course it is. When r equals 0, we do get the solution 0, 0, 0, 0, and that definitely should be a solution to this system. But there's others. There's infinitely many others. We'll talk a lot more about homogeneous systems. So that's a phrase that or a term that you want to remember. So I just want to emphasize something I mentioned as we were working through this example. If a homogeneous system has fewer equations and variables, there will be many solutions. You're guaranteed that. But only does that guarantee hold in a homogeneous system. In a typical system, you could have fewer equations and variables and still have, like say parallel lines or parallel planes that never have a solution. But in a homogeneous system, you always have at least one solution to the set, and that is, the zero vector. That will always work for a homogeneous system. So in a homogeneous system, you never have no solution. There's always at least one solution. And if there's at least one solution and you have fewer equations than variables, you're going to have a lot of solutions. So let's reflect on some of the things that we learned in this section. We learned what reduced echelon form even is, and we talked about using our calculators to find that. On the calculator, it's called reduced row echelon form. We spent a lot of time using parameters, learning to use parameters to describe dependent systems. And remember, dependent systems are the ones with many solutions. And we introduced the term homogeneous and what it means for a system of equations to be homogeneous. All right, a lot of good material in this section.